Great, thanks so much. There's a bit of feedback if maybe, okay, that's better. Thank you so much, and thank you for the invitation to join this really interesting meeting. I'm pleased to be able to share with you all some of the work that I've been doing exploring parametric finite temperature equations of state in binary neutron star merger simulations. So to start, by way of motivation, I want to highlight the kind of wide range of equation of state parameter space that a binary neutron star merger probes. So earlier this morning, we heard a really extensive overview of constraints on the cold, dense matter neutron-rich equation of state from Raithel. But binary neutron star mergers extend beyond this equation of state. They, of course, probe very dense matter, but during the merger itself, the matter in the system is raised to temperatures of some tens of MeV through shock heating, at which point the thermal pressure can contribute a significant fraction to the overall pressure budget of the system. Additionally, at late times in the merger system, the matter can deviate from the initial beta equilibrium composition. And so really a binary neutron star merger from the merger onwards is probing a different region of the parameter space than is probed with observations of the in-spiral. And so when it comes to performing numerical simulations of a binary neutron star merger into this post-merger phase, we need really good equations of state that can describe matter not just at high densities, but also arbitrary proton fractions and high temperatures. And so one way in which this is typically treated, as we've heard in some of the last talks in simulations, is to employ a finite temperature composition dependent equation of state table. And there's a number of these that exist publicly available in the literature, and the properties of some of these commonly used publicly available equations of state are summarized in these two slides, where on the left I'm showing the mass radius diagrams that correspond to the zero temperature slices for these kind of standardly used publicly available equations of state. And so one thing that I want to highlight here is that these sort of probe a limited range of this total parameter space. As we heard in Raithel's talk this morning, there's a lot of observational evidence that suggests that neutron star radii might be between about 10 and 12 kilometers, where you'll notice there are not any equation of state tables that probe that part of the parameter space. Additionally, these equations of state differ not only in their zero temperature properties, but also in the finite temperature part of the equation of state, which is shown on the right plot here, where you can see that already by the saturation density, there are differences of a factor of 5 in the thermal pressure for this sample of equations of state at a given temperature. And so when it comes to comparing two different simulations that use different tabulated equations of state, there are a lot of moving parts here that are actually changing between these simulations. Not only do the equations of state differ in their radii, their maximum mass, but they're also differing in the finite temperature part of the equation of state. And so in an effort to try to be able to disentangle those different moving parts and also to allow us to explore a wider range of the parameter space, we've developed a new framework for calculating the equation of state at arbitrary temperatures and proton fractions, which is based just on a simple series expansion, which is summarized here. And the philosophy of this approach is that it allows you to start from a simple cold beta equilibrium equation of state, which could be microphysical, or it could be simple piecewise polytropes that allow you to probe some new part of the equation of state parameter space. And then we add a thermal correction to go to finite temperatures. And the complete model also allows you to add in a composition dependent correction term to go to arbitrary proton fraction. But I'm just going to talk about the first part of the model here today. And so this gives us a schematic picture of what the thermal pressure looks like across the different regimes that we care about simulating in the neutron star merger simulation, where of course the very dense matter that is most interesting in a merger simulation is highly degenerate. And so in this degenerate regime, you can see that compared to, say, the prediction of the thermal pressure for an ideal fluid, which would rise just like NKT. In the degenerate regime, some of the available free energy of the system goes into interactions between particles, which leads to this characteristic reduction in the thermal pressure. And so the goal of this model, of course, is to include all of this relevant physics in our thermal correction term. And this should be contrasted with the hybrid approach, which is also kind of used in the literature as and is similar to the box expression I have shown here. But in the hybrid approach, by using a fixed thermal index here, This is really just the same as taking this ideal fluid approximation to very high densities, which you can see even in the schematic model, and you'll see again on the next slide, significantly overestimates the thermal pressure and is not including these more realistic effects. Okay, so to model the thermal pressure in the degenerate regime, we adopt a Fermi liquid theory-based approach, which is summarized here. But the key thing I want to highlight is that in this regime, basically the dependencies boil down to a dependence on the density and the temperature, and additionally this parameter m star, which is the effective mass of the system. We're just considering simple NPE matter. And so the effective mass, of course, if you knew your complete Lagrangian that describes all of the particle interactions of the system, you could calculate this mass function exactly. But we don't want to require that level of detailed physics a priori before that would basically restrict you from being able to apply this to kind of any parametric cold equation of state, which is the goal of this approach. And so we find actually that a new simple 2-parameter approximation of this effective mass function, which we call the m star approximation, is actually sufficient to reproduce these realistic calculations of the thermal pressure quite robustly. And so the 2 parameters briefly are just a density transition parameter and this power law parameter alpha, that characterizes kind of the decay of the effective mass function. And loosely, these can be interpreted as parameters related to the onset density of degeneracy and a particle related to the strength of the interactions within the matter. So you can see the performance of this model on the right here, where the diamonds are showing one of those realistic finite temperature equations of state. The dashed line is the hybrid or ideal fluid-based approximation, which vastly overestimates the thermal pressure. And then the solid line is our complete model for the thermal pressure, including these 2 extra free parameters, which, as you can see, does a really robust job of recreating the thermal pressure in densities and temperatures of interest. And so now that we have this framework for modeling the finite temperature part of the equation of state, we can start to explore this parameter space and ask ourselves, how do those uncertainties in the finite temperature part of the equation of state translate to neutron star merger simulations? So I'm going to show you today some results from a parameter study that I've done with Vasilis Pascalidis and Fariel Ozel, both at the University of Arizona. And so these simulations are for equal mass binary neutron star merger simulations. And in all of the simulations, I'll show you the neutron stars are governed by the identical cold equation of state, to which we add different sets of m star parameters that were designed to bracket the range of uncertainty shown in the finite temperature part of the equations of state for those tabulated models. And so these simulations are done, of course, in numerical relativity with the Illinois group code. I'll go ahead and show you an animation of what they look like. So on this slide, on the left, you'll see the evolution of the density of the neutron stars, and on the right, the thermal pressure. As you can see, the stars start at 0 temperature, and in fact, they remain quite cold up until the merger, as we would expect. But from the merger onwards, there's this shock heating at the merger itself, which raises the thermal pressure in this post-merger phase to quite high values relative to the cold pressure by late times. So this animation was just for one set of m star parameters. We can also compare these late time snapshots for the different parameters in our survey. And let me just jump ahead and highlight a couple of the key trends that we're finding. So now I'm showing not just the thermal pressure, but also the temperature, which we're able to extract exactly because this is a microphysically based framework. And so I'll just highlight here that we do identify a couple interesting trends. For example, that this density parameter, which is related to the onset of degenerate effects in the matter, seems to be governing primarily the thermal pressure in the outer layers of the neutron star remnant, while the power law parameter alpha is more directly governing the core temperature of the remnant. And this is just a first look, because this is a simple 2x2 parameter study, but this really is giving us a first look at how the parameters of the finite temperature part of the equation of state are governing different regimes of interest in the post-merger thermal properties. And so we can look at not just the spatial distribution, but also the densities at which these high thermal pressures and temperatures occur, which is summarized in this plot. And you'll notice that, again, I want to emphasize that we're reaching pretty high thermal pressures in these simulations, which is consistent with what's been found before. But I want to highlight here that the thermal pressure exceeds 10% of the cold pressure at densities up to 2 to 3 times the nuclear saturation. So this is a significant player in the post-merger evolution. And we find differences of up to a factor of 5 depending in the thermal pressure, depending on the choice of M-star parameters, while the temperatures vary by factors of 2 to 3. And it might seem redundant to look at thermal pressure and temperature separately because of course these are functions of each other, but they give you a slightly different intuition for how these thermal properties are going to map to potentially observable properties. So of course, because the thermal pressure adds to the total pressure budget, this is going to affect the oscillations of the remnant and the dynamics of this post-merger phase, whereas the temperature is going to most directly affect the neutrino emissivities and subsequent cooling or irradiation of the disk. And so finally, we can also look at the gravitational wave signatures that are extracted for these different finite temperature parameters. And as you'll see from the slide, the in-spiral portion of the waveforms are identical in all cases, which is what we would expect, given that we didn't see any significant heating until at the merger itself. And so it's only after the merger when we have heating that these differences in the finite temperature part of the equation of state are activated. But we do find differences in the post-merger signal, not only in the amplitude, but also the decaying beat frequencies on this post-merger gravitational wave signal, which is hinting at differences in the oscillations of the post-merger remnant that are sensitive to this finite temperature part of the equation of state. And so this raises the really tantalizing possibility that we might be able to measure these M-star parameters, or more generally, we might be able to probe the finite temperature part of the equation of state, which is inaccessible with observations of the in-spiral using a future detection of post-merger gravitational waves. And I'm going to leave this as a question for now, because there's a lot of follow-up work we're doing on this. I see I'm just about out of time, so let me just conclude by saying the M-star framework is not just used to study finite temperature parts of the equation of state, but can also be used more generally to study new parts of the zero temperature or cold equation of state parameter space, using realistic effects that include the leading order effects of degeneracy. And also critically, this framework allows you to, when you're doing a systematic comparison of different cold equations of state, to ensure that the finite temperature part is the same for those different models. So you can do really systematic comparisons. And so I'll just advertise there's one such study that I'm involved in that's going to be coming out on arXiv tomorrow. And so with that, I'll just put up my summary slide and happy to take questions. Thank you.
Okay, thank you for Todd. Very interesting, tightly reasoned talk. And do we have any questions? Well, I can see one from Wolfgang.
Yeah, that is indeed a very interesting developing. And so I have one question about these different post-merger oscillations. So in some studies, one can see that in a rotating frame, merger remnants have this very characteristic structure, which is also featuring some sort of tail. And people looking at thermal evolution, like I did, sometimes see some also hotspots in these regions. And that was actually a question if the thermal pressure is relevant for this kind of structure. So have you looked at the thermal structure in the remnants, if this differs between these two prescriptions?
So you mean,
and if you see these patterns?
Beyond these kinds of profiles that I was showing? So we do also look at like the rotation profiles within the stars, which do differ somewhat between these different prescriptions. That's in the full paper. I'm not sure if I follow what aspect you're asking for, though.
Yeah, so sometimes one can see in a co-rotating frame, when averaging out radial oscillations, some relatively stable structure that is maybe not too visible if just looking at snapshots.
I see. No, we did not look at that, but that's an interesting suggestion. Thank you. I'll take a look again at your papers, which I've seen before, but thank you.
Okay, and one last question before we break for lunch from David.
Thank you. Yeah, very nice work. I was curious to know how big of a difference do you see in the peak frequencies in the post-merger with these models?
So we don't report the post-merger power spectra, in part because of some numerical issues at late times with the convergence. from the piecewise polytropes, not from the finite temperature part of the equation of state, we suspect. So we're following up on this right now, and hopefully we'll have a more conclusive answer for you in the coming months. But this is why I intentionally left it a little bit as a question here, because we're working on quantifying that answer a bit more robustly than we're currently able to, and also extending this. This was all for one cold equation of state, but you would expect this to vary with the neutron star compactness, of course, which is going to determine how much shock heating there is. And so we're working on also answering those questions in the coming months, but hopefully I'll have an answer for you soon.
Thank you.
Okay, I'd like to thank all the speakers this morning and all the participants in the discussion.